So addition reactions, let's have a think about some addition reactions. We did some work on this yesterday. So if you were here yesterday, think back to the stuff we did on alkenes versus benzene. Alkenes and pi bonds is what I meant to say. And we can now think about this same theory in terms of benzene. So alkenes can undergo addition reactions where you add something across a double bond. An addition reaction is where you start off with two or more reactants and you end up with one product. So you're adding things together to perform one product. In this case, we've added a halogen to the carbon-carbon double bond in an alkene to form in this case, dihalogenoalkane. Why are these? Why do these happen? And why do they happen easily? Why is a double bond much easier to add an electrophile to, for example, than an alkane? What is it about the double bond? Or specifically the double bit of the double bond? So the double bit of a double bond is electron density that exists above and below the plane of the bond. That means that they're quite diffuse and they're quite far away from the bond. Sigma bonds, because they lie in orbitals that point at one another, tend to be a little bit closer to the bond, to the plane of the bond, whereas pi orbitals tend to be a little bit further away. Or pi bonds, sorry, tend to be a little bit further away. That means makes them, an area of high electron density, which is easily attackable. So they are susceptible to attack from electrophiles. We'll very briefly go over the mechanism. So if we have a chlorine molecule, chlorine molecules are not polar, not innately polar, because chlorine has the same electronegativity as another chlorine atom. So the split between the electrons is going to be nice and even, nice and equal. Split between the electrons. Sorry, the electrons are going to spend their time fairly evenly between the two chlorine molecules. So there's no polarity, there's no dipole across the bond. But when a chlorine molecule comes close to an area of high electron density, the negative electrons in the high electron density are going to repel the electrons in the bond and induce a dipole. We did cover this yesterday, but I'm just briefly going through it again. They can induce a dipole. Oh, I've done that the wrong way around. Sorry. It should be delta positive, that one. Should be delta negative. Then you can get transfer of the pair of electrons from the nice electron-rich double bond to that delta positive chlorine, because they're going to be attracted to the positive charge that has appeared. And then the pair of electrons that's in the chlorine-chlorine bond can move to spend all of their time around one chlorine, making it a chloride ion. That means this species here, let's do it in a different color, the chlorine is accepting a pair of electrons. What does that make it? It's accepting a pair of electrons. And this is the attacking species. So the attacking species accepting a pair of electrons, that makes it an electrophile. That is why this is electrophilic addition, because we have an electrophile. Let's write electrophilic addition somewhere. Electrophilic addition. We're not going to finish off the mechanism because we did it yesterday. Okay, why is this important, or why are we interested in this? Because it's simpler. Nothing's ever simple in A-level chemistry, is it? But it's simpler when you think about it in terms of addition reactions with alkenes than it is when you apply it to benzene. But it's the same principle, okay?